Okay, just looking at, not actually going to work out examples, just looking at what can happen with rational functions now, the form ln over ln times quad, being the linear factor in the numerator, a linear factor times an irreducible quadratic factor in the denominator, or ln over ln times ln, which would be linear factor in the numerator, 3 linear factors multiplied in the denominator. So, ln over ln times quad, we're going to find the zeros of the numerator and mark as zeros of r of x. Now I don't have a specific example, but let's just pick a point. Let's see, I'll move this back and forth till I hear something. Well, it's real quiet here, so I don't know what I'm hearing, so I'll stop here. Okay. So let's say this is a 0. Of the numerator. And then there's only 1 0 of the denominator. So the numerator has 1 0. Denominator has exactly 1 0. This quad factor is irreducible. So where's the 0 of the denominator going to be? It could be to the right or the left of the 0 of the numerator. Doesn't really matter much whether it's to the right or left of the y-axis, but I'll just put it over here for you. Okay? You can think about, what if I put it over here? What if I put it really close to the 0 of the numerator? Play around with the ideas. Okay, so here is your 0 denominator would be here. You'd have a vertical asymptote. Okay? Now the quadratic form is always either positive or always negative, so it's not going to cause any change in the sign of the function. So the 0 of the denominator will cause a change in sign. The 0 of the numerator will cause a change of sign, although you can work out the signs carefully. You might not totally understand why that is, but if you think about it, I think maybe you can. So the point is now, if I know what the sign of the y-intercept is, I can figure out everything else. Excuse me. So the y-intercept could be either above the x-axis or below. Let's say that the y-intercept is here. And we know how to get the y-intercept. We just plug 0 in for x and take what's left. Okay, so here's our y-intercept, which means now that the function is negative from here to here. So I don't know whether the ln in the numerator is positive or negative, or the quad is, or whether ln denominator is, but I know that when I take all the signs, I'm going to get a negative. So I'm just going to say it's negative on this interval because it's negative here. Okay? Now to the right of this, well, if it's negative here, it's got to go positive here. And same here. It's going to have to be positive here. Now, the end behavior, if you multiply out the numerator and multiply out the denominator. Well, there's nothing to multiply out here. Numerator has either an x or a negative x. Okay? So that could be plus or minus an x for the leading term, the highest power term. Remember, it's going to be sometimes x plus something, and the something you add becomes insignificant when x gets really big. You multiply these out, you're going to get an x cubed for the leading term, maybe a plus, maybe a minus. And the x squared and the x and the other term don't amount to much if x gets big enough. So this is going to be an x over an x cubed. It might be a plus or a minus. That's going to be a plus or minus reciprocal square, which, as you know, has this sort of behavior. Now, for smaller x, it doesn't behave like this, okay, because this only applies when x is really big. But this means that we're going to approach the x-axis the same way on both sides. In other words, either both from above, or if it was negative 1 over x squared, you'd have this thing upside down. It would approach the x-axis from below. Okay, so in this case, it's positive here and positive here, so it will approach the x-axis from above, meaning that to the left of this asymptote, it's going to behave like this. And then to the right, well, it goes negative. So it's going to be down here. It's going to come up from down here. It's going to go through the y-intercept. It's going to come back up here and go through the axis, here, the x-axis. Then it's going to continue getting bigger for a little while, but it's got to become an asymptote with the y-axis, so it's going to come down like this. So the graph is going to have sort of this behavior. And all the little curves and wiggles are things that you have to use calculus for. Is there an inflection point here? Is there an inflection point to the left of here? Maximum, minimum, any inflection points over here? We don't know. We can't figure it out. So just ignore what I just said. You don't even have to know what an inflection point is. But since I mentioned, it's a point where the thing goes from concave down to concave up. Okay. Then their second derivative is 0 at that point and so on. Okay, so that would be this case. Now a linear over linear times a linear times a linear. And I'm just going to draw this and say it because you're probably getting tired of watching this anyway. But, think about what I'm saying here. Okay, there's 1 0 of the numerator. So stop at a random point. We'll stop over here this time. So there's a 0 of the numerator. Zeros of the denominator, you're going to have 1 for each limb. Now, assuming they're all separate, they don't have to be. You have 1 here, well, that should be a dotted line. You have 1 here, and you have 1 on the other side of this 0. Okay? And you're going to have a y-intercept. Above, below, medium, medium, minor, down, below. Now, last one was below, we'll put this one above. Okay? So, zeros of the denominator give you vertical asymptotes. Okay, well, between this vertical asymptote and this, there are no zeros. So since the value is positive at the y-intercept, which is between these two, we know that we're positive in this interval. All of these are linear, and when you work it out, you'll find that we do change the sign as we approach as we go to the right of this asymptote, okay? And we change the sign here, so it's going to go negative in this interval, meaning it's going to be
left all doors open again.
positive in this interval. And wait a minute, I'm looking between the asymptotes, okay? You have an interval from the asymptote to the zero of the numerator. That's going to make it negative here, then it's going to change to positive here, and it's going to be negative here. The thing that tipped me off, I'm glad I didn't go on with it, is it has to be the same here as here, because the degree of this thing, it's like a 1 over x squared again. So it's like 1 over x squared, so it's either a plus or minus. And in this case, it's minus, because it's negative here and negative here. So it's coming up toward a 0 here, coming up toward a 0 here. So you're going to have asymptotes below the x-axis. Okay, well, now that we know this, we have an asymptote here and an asymptote at the x-axis. Asymptote has to be below the x-axis, so we've got this. Then it's positive in the next interval. So we're going to come down from an asymptote up here, down through the 0, and then we're going to go negative and approach this asymptote. So we're going to come down here like this, and then we're going to approach this asymptote. Okay. Now we're positive between here and here, and we've got asymptotes. So we've got to be up here. We're going to come down through here. We're going to come back up here. And then to the right, we've got an asymptote with the negative x-axis and a vertical asymptote. It's going to be like this. And there's what a graph of a lin over lin might look like. Now, if you've got the sequence of the asymptotes different, for example, if this asymptote was over here, then the graph would look somewhat different. And you wouldn't have a 0 between two asymptotes then, if this asymptote happened to be over here. Okay? So you wouldn't have any place where the function does this. It's inevitable with 3 vertical asymptotes and only 1 0 that between at least 2 of those asymptotes you're going to have something that acts like this. So you might want to think about that. You want to think about those things if you can. This procedure will lead you to these conclusions. Now, there is more to it. Sometimes we have identical lins with at least linear factors with the same zeros in the numerator or denominator, and they behave differently from numerator and denominator. So we've kind of got to be careful how we graph those, and we're going to talk about that a little bit. But for right now, if we understand this, we're not doing too badly. Basic thing, focus on the procedure. Don't memorize this is what happens in this case and this is what happens in this case. Follow the procedure and see how it happens. And of course, for homework, I'll give you some examples. It's easy to find the zeros, so it's pretty easy to set this stuff up.